everyone, welcome to my YouTube channel. I invite you today to join me on a venture of exploring one of the groundbreaking works in the field of chemistry. Sharpless, Bertozzi and Meldon. Does it ring a bell? So without wasting much time, let's get going in this very first video.
So we are here in the first session on click transformations in chemistry, an area within chemistry that has gained quite a sight in pharmaceutical and medicinal sciences, nano and polymer sciences and so on, due to its remarkable ability to click through substrates and form a new entity under simple conditions. An immense contribution has been made by Sharpless in this particular area, followed by other pioneers.
Click reaction, in a general definition, there is no particular definition as such of now, but a general definition of click reaction is that any reaction that can produce conjugate molecules efficiently from smaller units under simple reaction conditions. Carl Berry Sharpless, as you can see here, is an American stereochemist and a two-time Nobel laureate in chemistry, renowned for his work on stereoselective reactions and click chemistry. Like mentioned earlier, Sharpless, together with other two pioneers, they have worked on a reaction that have enabled to be very synonymous in click chemistry. So Sharpless and Meldon, they independently worked on copper catalyzed cycloaddition reaction. They developed triazones from alkynes and azides using copper catalyst, but independently. Bertozzi, on the other hand, she worked on similar reaction, but the only difference was she worked on metal-free version of this reaction. So the benefit of that was more so tilted towards bioorthogonal chemistry. So together these pioneers became well renowned in both these domains, click chemistry and bioorthogonal chemistry. So what is the criteria for a reaction to be click reaction? The reaction must be modular, wide in scope. It should give very high yields. If at all byproducts are generated, then it should be easily removable by non-chromatographic methods. And above all, the reaction should yield good stereospecific product. So as mentioned earlier, click reactions, they mostly work on the principle of cycloaddition reactions. So what are cycloaddition reactions? These are basically reactions wherein two or more pi electron systems react to form a ring at the expense of one pi bond. They are classified based on certain conditions, namely number of electrons that participate in the reaction, nature of the orbitals that change, and the stereochemical mode of cycloaddition, meaning whether the addition would be suprafissional or intrafissional or whatever the same. Now, the reactions, like namely over here, there are different type of cycloaddition reactions, 2 plus 2, 4 plus 2, and many more. So, these reactions are kind of governed by selection rules. Selection rules, in general, they help to know whether the reaction will be allowed or forbidden under thermal and photochemical conditions. And uh, there are certain theories that are utilized to build this selection rule or to tabulate this selection. So the theories are frontier molecular orbital theory or FMO, Woodward-Hoffman rule, correlation diagram, and Huckel-Mobius theory. How these theories are applied in formulating the selection rule for cycloaddition reaction is currently not much of interest. What is of our interest is the 1,3 dipolar cycloaddition reaction. Now, 1,3-dipolar cycloaddition reaction was very first introduced by Houston in 1960. And this reaction, it follows syn addition, meaning addition from the same side. What were the requirements of this reaction? First is 1,3-dipolar species. Dipolar species as in a species which has both the charges within the same molecule, or in other words, electrically neutral species, like azoxy, ozone, or azides. And you require a dipolarifier. A dipolarifier as in any dipolar compound like alkenes, alkynes and all, which has delocalized electrons over three atoms. So now let's see certain cycloaddition click reactions. So this is a kind of very historical advancement, and it is very interesting as well. The first is Staudinger and Traceless-Staudinger ligation click reaction. Over here, by clicking azide with phosphines, amides, that is a new peptide bond was formed. So Staudinger ligation was on clicking azides with ester phosphine to make amides. And what is the difference, or how is it different from traceless Staudinger? If you notice, in Staudinger, a normal ester phosphine is used. In case of traceless Staudinger, thioester phosphine is used with azide to yield the product. Now, why this change? Because if you see, in former case, the phosphate group is attached with the peptide, with the molecule that is desired. This in turn uh, decreases the product yield drastically because phosphate is not really easy to remove, and this is not what is desired as well. In the latter case, because thioester is what is introduced here, so we are getting the amide, that is the new peptide bond, effectively in larger yield, and the phosphate group is also easily separated. And uh, being separated, it can be easily removed. So this was the advancement. Later, after traceless Staudinger, came azide alkyne Houston 1,3-dipolar cycloaddition reaction. So this reaction was a kind of hallmark because the other reactions on which, like mentioned earlier, Sharpless, Melton, and Bertuzzi, they had worked on this particular reaction only differently. So understanding this reaction is very important. Basically, it is a very simple reaction, an azide molecule with an alkyne at a certain reaction conditions. It gives you triazole. But if noticed, over here we are getting a mixture of the product. We are getting a mixture of the regioisomer of the triazole. So again, now to get a specific product, there came another um, next advancement, and that was copper catalyzed. Copper catalyzed click reaction or COOC is basically a reaction wherein copper catalyst is used to mediate the cycloaddition reaction of azides and alkynes. So over here, it is very evident that one specific regioisomer of triazole is formed. Now, copper, if you see, it is quite toxic. This reaction, if you want to introduce into a living organism, for instance, it will be very, very, very um, challenging because of the metal that is used. Metal itself will be very toxic to the living organism. So now if we want to induce this reaction within the living organism, what to do? So we'll have to eliminate the metal. So how to do that? So this is exactly what was the questionnaire that was going around, and therefore there came the next advancement in the reaction, and that is spark. Strain promoted reaction, strain promoted click reaction, wherein the metal criteria was eliminated. Instead, a strained molecule was used. A strained molecule was clicked with azide to form the desired product. But now, what was the disadvantage over here? we have eliminated metal. But the problem was that due to the strain factor, the reaction rate decreased drastically. In case of copper catalyzed reaction, the reaction rate is mediated at a faster rate due to the copper catalyst. It is because of this reason that even today in click chemistry, quark reactions are very profound over spark. Now, how to eliminate the strain factor? So to eliminate this strain factor, many other metal-free click reactions became advanced. Like they started developing. So we are having one this thiol-based click reactions very much in recent trends. One of the uh, bunch or collection of click reactions under metal-free click reactions. And majorly over here, thioethers, dithioethers, thiocarbamates, alcohols, such molecules are synthesized. For instance, over here we have different classes of thiol-based click reactions. We have radical nucleic reactions, meaning reactions that can be mediated via radical initiator or through light. Then we have nucleophilic addition click reactions, meaning with the help of a nucleophile, the reaction is getting mediated. We are having nucleophilic substitution reactions as well. So example, if you take of thiol isocyanate, in reports, in literature, this thiol isocyanate click reactions have been used to generate polythiourethans, which is a sulfur analog of polyurethane. So likewise, all these reactions, they have marked quite a beautiful uh, landmark in the development of click reactions. If you observe thiol epoxide and thiol isocyanate, thiohalogen, so these are all click reactions between two functional groups. In later slides, we'll come across that normally in reactions, it is not very easy to bring two molecules together with favorable functional group. Over here, this is very uh, new, and it is very interesting that the two functional groups are itself just being clicked with each other to form a new molecule. So this is a very good point to be noted. Other miscellaneous like reactions, we have spring-loaded reactions, which is results from strain in the ring system. Again, it was introduced by Sharpless, and many nucleophilic ring opening reactions of epoxides, aziridines, they all come under this class. We have non-aldol carbonyl type click reactions, wherein hydrozones, amides, isourea, and all are formed. Oxime-based click reactions, these are quite useful in forming hydrogens and cell adhesion as well. We are having other reactions as well, including the ones wherein you introduce a functional group to carbon-carbon multiple bonds, leading to three-membered rings. So far we have been through some historical advancements in cycloaddition click reaction. Now let us see recent advancements in click chemistry and their leading role in various applications. So let's take one example to understand how click reactions are useful. Have you ever heard of block copolymers? In very layman terms, these are polymers formed linearly. That is, something like this. Right? We have one polymeric group, then we have another polymeric group. So this attachment like that, linearly, these are block copolymers. Block copolymers are very instrumental in formulating nanostructured materials. They are also very much useful in biosensing, cell and tissue engineering, drug delivery systems, and so on. Now consider the synthesis of block copolymers. Normally, there are two routes. One route that involves the sequential addition of different monomers through polymerization, and the other route that involves linking different polymeric chains via some functionality. Now, if we ought to compare the two routes, which one would be preferred the most? As per the literature, the route that involves linking different polymeric chains via functionalities, that route would be very preferable. Why? Due to the lack of efficient linker chemistry. So, the deal over here is that at times, one polymeric group would require one functional group. Other polymeric group would desire some other functional group. Now, if we wish to bring that same two molecules together, how to do that? Because both the polymeric chains are preferring other functional groups, different functional groups. So how to bring them together? So this was the problem. So how are click reactions useful? For once, click reactions can tolerate various functional groups. Additionally, it can give extremely high reaction efficiency. This property of click reactions has enabled it to become the hallmark of linker chemistry. It is one of the most efficient ways to join two substances together and has thus been used repeatedly to link well-defined homopolymers to form block copolymers. You'll find more such examples in literature as to how click chemistry is regarded as the most powerful tool for pharmaceutical and polymeric such applications. So the other example is of incorporating lanthanide series in preparing highly efficient functionalized materials. And how was that achieved? Again, the lanthanide elements, preparing lanthanide complexes and linking it to the polymer matrix via a metal-free click reaction. So again, this did had a very good impact on synthesizing a very good functionalized polymeric material as reported in the literature. So there are many such examples that you'll find. With this, we come to the end of our discussion on click chemistry. There are a lot miles to go, so the journey has just begun.
So with this, we are at the end of our first session. I hope you enjoyed this venture with me as much as I did. If you want to explore more, do subscribe to my channel and hit the bell icon. See you in the next video.